Okay, so welcome back to another lesson with Miss B, and we're going to be doing the Physics CSEC paper, May June 2025. Okay, so it starts off with question 1, and of course it's a graphing question. It says an electric hot plate rated at 240 volts and 3.5 amps is used to heat 600 grams of liquid. The liquid is heated and its temperature is recorded at 20-second intervals. The results obtained as shown in Table 1. So here we have the temperature readings for the liquid when heated. Using the data recorded in Table 1 and the grid provided in Figure 1 on page 5, plot a graph of temperature degrees Celsius against time in seconds. Then it says to draw the line of best fit through the last 5 points, that is from 120 seconds to 200 seconds, and this is 8 points. So the graph was drawn, and I did every 10 spaces 10 units, every 10 spaces 10 units, and the y-axis, was on the right hand side. I labeled my y-axis temperature in degrees Celsius, and then I did the x-axis, and I did every 5 spaces I did 20 units. And it was easy because it was just every 20 and you could plot on it. You didn't have to guess anything. And so I plotted all my points. The last 5 were the best set of points. And then of course, you're going to have to find a gradient. So we put the straight line between these last 5 points. And I was able to find 2 points along the line that passed through the crosshairs. And I got the first point to have coordinates of 80 degrees Celsius and 220 seconds, so the y-x coordinates. And then for the second point, I got it to be 42 degrees Celsius and 108 seconds. That was my second point. Then, of course, for gradient, you have to do the change in y with the change in x. So I subtracted 42 from 80, then divided it by the difference of 220 minus 108 seconds to get 38 degrees Celsius over 112 seconds. And from there, we got the gradient to be 0.339 degrees Celsius per second. Now, of course, we had to move all of this up here in the space provided. You can't leave it on the graph. Okay, now that that was done, we were supposed to use the information given in the excerpt question 1. So that's why I underlined everything that they gave us. They gave us 240 volts, 3.5 amps, and the mass of the liquid. And so down here it says, calculate the power of the hot plate in watts. So the power of the hot plate in watts would be power equal to current times voltage. So P equals to IV. If current is 3.5 amps and voltage is 240, just multiply the 2, we get 840 watts. Then assuming that all the energy from the hot plate is transferred to the liquid, you have to calculate the energy in joules absorbed by the liquid in the last 80 seconds. We get power is equal to energy over time. If power is 840 watts and the time is 80 seconds, then energy is equal to power times time, and so we multiply the 840 by 80 to get 67,200 joules. For the liquid, calculate the value of C, given that the power P is related to the gradient by the equation. P is equal to mcg, which makes sense. And then it says where m is the mass of the liquid. Express your answer to 3 significant figures. I didn't do that. So, well, remember that PT is equal to MCAT. And since the gradient already has in the time, they just put P equal to MCG, right? And so they said 3 sig figs. I would have cried if I found out I didn't finish this. So 3 sig figs would be 413, 430 joules. They really try to test your understanding in this one. But it was pretty straightforward, this question. So we have here 4,130. That's 3 sig figs. There's no point, so the 0 is insignificant. And that will be the final answer. So maybe I can just get rid of all of this here. So the final answer is 4,130 joules per kilograms degree Celsius. Then the last question of the question 1, the last question, our last part of question 1, we have complete table 2 by inserting the symbol and SI unit for the quantities involved in the experiment. And we have here small c, that's specific heat capacity. We have joules per kilograms per Kelvin, or it could be per degree Celsius. But this I want the SI unit, so let's just stay with Kelvin. And then heat capacity, that would be a capital letter C. 2. Define the term gravitational potential energy. This is the amount of energy stored by an object due to its position in a gravitational field. It is measured in SI units of joules. Figure 2 shows Keyroy, a basketball player in the National League in St. Vincent, going through his routine. As Keyroy dribbles the ball with either his right or left hand, energy conversions take place. List the energy changes which take place through the following stages as he dribbles the ball. So when the ball leaves his hand and strikes the ground, we go from gravitational potential energy to kinetic energy, to sound energy, to heat energy. Then they said, while the ball is in contact with the ground, so we have some kinetic energy, then elastic potential energy, which is the rebound of the ball, then the sound energy, then heat energy. When the ball leaves the ground and rebounds to his hand, we have elastic potential energy, kinetic energy, then gravitational potential energy. In a test to determine if a basketball with a mass of 1.1 kilograms is properly inflated, the basketball is dropped from a height of 1.5 meters and rebounds to a height of 0.8 meters. Calculate the energy lost by the basketball. So the potential energy before, using E equals to mgh, was equal to 16.5. So remember, the mass stayed the same, but the height was different. So the first height was 1.5, so it had potential energy of 16.5 joules. And then on the rebound, it had a height of 0.8, and therefore its potential energy was less. It was 8.8. So the change in energy, or the energy lost, would be the difference in 16.5 and 8.8. You get 7.7 joules. So just 2 possible ways in which the energy was lost by the ball. 2 possible ways in which energy may be lost by the ball are sound and heat due to friction. Okay, so moving on to question 3. It says to draw and label a diagram of a simple transformer. So you need to include the soft iron core, the alternating current on both sides, and the primary and secondary coils on the transformer itself. With the aid of your diagram, explain the operation of a simple transformer. A transformer operates on the principle of electromagnetic induction. In a transformer, when an alternating voltage is applied to the primary coil, it creates a change in magnetic field in the soft iron core. The secondary coil of wires is not connected to the first coil of wires, so electricity is induced in this coil of wires by the change in magnetic field. Based on the ratio of the number of coils in the primary side of the secondary side, the transformer would either produce more or less voltage. They are called either step-up or step-down transformers, respectively. Then it says a local power station distributes power at 13.2 kilovolts. This power is then converted to 220 volts for domestic use. Based on the scenario above, identify the key assumption made with respect to an ideal transformer. The key assumption of ideal transformers is that no energy example, heat, sound, or magnetic leakage, is lost, hence it is 100% efficient. Therefore, power in is equal to power out. State the equation for an ideal transformer. Power in equals to power out, hence current times voltage in the primary coil is equal to current times voltage in the secondary coil. Assuming the transformer is ideal, calculate its turns ratio. In the primary coil, we are given the voltage, which is 13,200 volts. We convert the kilovolts to volts. And in the second coil, the secondary coil, we have 220 volts. So if NP over NS is equivalent to VP over VS, we can solve for the turns ratio by dividing the primary value by the secondary value to get 60. So the turns ratio would be 60. If the current in the secondary coil is 5 amps, calculate the current in the primary coils. So the primary coil, we have the voltage of 13,200 volts, and the current is what we're looking for. The secondary coil has a voltage of 220 volts, and the current is 5 amps. So if VP times IP is equal to VS times IS, then VP over VS is equal to IS over IP. Therefore, IP will be equal to VS IS over VP to give you 0. Well, as we substitute, we're going to substitute 220 volts times 5 amps divided by 13,200 volts, and we get 0.083 amps. Now remember, the goal is to minimize energy loss, especially in the form of heat loss in transporting current. So a high voltage is used to transport low current over long distances via these industrial transformers, so that a high current at low voltage can be used in the house. Okay? Define each of the following wave phenomena. Wavelength. A wavelength is a distance between two corresponding points on consecutive waves, such as crest to crest or trough to trough. It is measured in SI units of meters. Then we have amplitude. The amplitude is the maximum distance of a crest or the depth of a trough from the rest position. It tells us how much energy the wave is carrying. It is measured in SI units of meters. Diffraction is the bending and spreading out of waves when they pass through a narrow opening or around the edge of an obstacle. When the gap is about the same size as the wavelength, diffraction is more obvious. So I drew it out. So we have wavelength. Wavelength could be from crest to crest, trough to trough, or from the beginning of a crest right around to the end of a trough. And then for amplitude, it's from the rest position to the top of the crest, or from the rest position to the bottom of a trough. And then diffraction would be have your wave fronts hitting on a gap or meeting a gap, and then the gap, if the gap is small enough, the spreading of the waves will be very obvious and it will be nice to look at. Two loudspeakers placed about 1 meter apart are simultaneously playing the same music. Sophia walks along the line from A to B as shown in figure 3. Describe what Sophia hears while walking along the line from A to B. I find some of these questions were repeated from years ago. So at A, Sophia will hear the music very well, but as she walks the distance between the speakers, she will hear times when the sound is louder and times when it is non-existent. Explain your answer in B1. Of course. So sound is energy that travels via a longitudinal wave. Hence, it exhibits properties of a wave like interference in this case. At some points, the sound wave will experience constructive interference, and this is where the sound gets louder, and then at other points, the sound wave will experience destructive interference. This is where the sound will be lower or non-existent. Okay. Then it says, explain the concept of wave-particle duality of light, making use of the contributions of Newton and Young. So these two people were rivals in this. So light is both a particle and a wave, a concept known as wave-particle duality. This idea arose from centuries of debate and experimentation. Sir Isaac Newton in the 17th century believed light was made of tiny particles or corpuscles. This particle theory of light explained reflection and refraction well, supporting the idea that light travels in straight lines. However, in the early 1800s, Thomas Young challenged this view with his famous double slit experiment. When light was passed through two narrow slits, it created a pattern of bright and dark bands on the screen. And this phenomenon, called interference, is the behavior of waves, not particles. So, Young's experiment proved that light behaves as a wave. Despite this, some experiments couldn't be explained using wave theory alone. For example, the photoelectric effect, which was later observed, that could knock electrons off metal surfaces. And Albert Einstein later explained this by proposing that light is made of photons, which are tiny packets of energy like particles. So this duality explains why light can interfere and diffract like a wave, but can also deliver energy in quantized amounts, as seen in the photoelectric effect and photosynthesis. Define each of the following terms. Velocity. Velocity is the rate of change of displacement with respect to time. It tells us how fast and in what direction something is moving. It has SI units of meters per second. It is also a vector quantity because it has size and direction. Velocity is equal to displacement over time. Momentum. Momentum is the quantity of motion an object has. It is the product of its mass and its velocity. It has SI units of kilograms, meters per second. Momentum is equal to mass times velocity. State the principle of conservation of linear momentum. The conservation of linear momentum states that the total momentum of a system remains constant if no external forces act on it. Hence, total momentum before is equal to total momentum after. So the question in C deals with calculating momentum, and I always tell children to draw it out, otherwise you're going to make stupid mistakes. You don't have to draw out the actual drawings, but you could just make circles or squares. But circles make sense since circles move easier, right? So it says, in a 2020 cricket match, a ball with a mass of 160 grams has a velocity of 25 meters per second off the pitch and is hit by a bat with a mass of 1.2 kilograms moving in the opposite direction at 15 meters per second. Calculate the momentum of the bat before collision. So look at my drawing. I have the before, where I have the ball, and I have everything that they gave us. I have the ball, I have the mass of the ball in kilograms because you have to use the SI units, and I have the speed of the ball. Then I have the bat, I have the mass of the bat, and also they tell us that it was going in the opposite direction. So because momentum is a vector quantity, you have to include your signs to indicate direction, right? So it's moving in the opposite direction. And then they said that after, did they say after here? No. So I drew this after I read the whole question. So if you go down further, they would tell you that after contact between the ball and the bat, the ball moves in the opposite direction at 20 meters per second, assuming the collision is completely elastic, right? So we have the ball moving in the opposite direction at 20 meters per second. So it tells us what is happening. So I drew it out. The ball, the same mass, and the same is going in the opposite direction. So you put the negative sign. And then again, down below, you had to solve this x. So here I have this, and it says calculate the momentum of the bat before collision. So the bat has a mass of 1.2 kilograms, and it was going negative 15 meters per second. So we get the momentum of the bat to be negative 18 kilograms meters per second. And you put that answer on the line. So remember, your space is for your calculation, and the line is for your answer. The ball before collision. So again, we have the drawing here, and we have all the information we need. Remember, momentum is equal to mass times velocity. And so we multiply the mass of the ball, 0.16 times 25 meters per second. We get 4 kilogram meters per second. Okay, and then now it says after contact between the bat and the ball moves in the opposite direction at 20 meters per second. Assuming the collision is completely elastic, meaning that it bounced off of each other, the ball bounced off the bat, calculate the momentum of the bat after the collision. So remember, momentum before is equal to momentum after. So we add up everything before. So we get the negative 18 and the positive 4. And then we do a little calculation here. We have 0.16 times negative 20 plus 1.2 times x. So we need to find the velocity of the bat after. So since it's conserved, all we have to do is solve for x. And so we're going to we're going to subtract. We find that negative 18 plus 4 gives us 14. And so since 0.16 times negative 20 gives us negative 3.2, we're going to add it to this side. So we have negative 14 plus 3.2. They have the same units, which means we're going good. And then we're going to divide it by 1.2 kilograms. Hence, the speed of the bat will be negative 9 meters per second. Therefore, the momentum of the bat was negative 9 meters per second times 1.2 to give us negative 10.8 kilogram meters per second. Then you have to work out the velocity of the bat after the collision, which was negative 9 meters per second. 6. The final question. Table 6 shows the properties of the radiation emitted in the radioactive decay. And we had to fill in the blanks or the empty spaces on the table. So they gave us the alpha, beta, and gamma decay, or the alpha, beta, and gamma emission. And they tell us the mass. So we have to know the masses of these things. So the electron, which is a beta, will be negligible because it has mass. Whereas gamma radiation, it is just pure energy, so it'll be 0. The ionizing power decreases as you go down. So alpha particles are very strong at ionizing because they're so heavy. And then gamma particles, or gamma radiation, gamma radiation is very weak. Now, alpha particles are helium particles, whereas gamma radiation is an electromagnetic wave. Then it says, an equation for radioactive decay is shown below. They want us to solve the values of K and P and explain your response. So just think of this as just simply adding across the board. You have K, you have 14, and so you have 0, and this is going to be the equal sign. So K is equal to 14 plus 0, so therefore K must be 14. And then you have 6 now. 6 equal to 7 plus P. So what will give you back 6? You must have a negative 1, right? I don't see the negative 1 here. So let me fix it. So this should be negative 1 right here. And so we have the negative 1 here. Okay? So that's negative 1 right there. So K is 14 and P is negative 1. So it was just an addition, a simple addition. Then it says, using the equation of radioactive decay given on page 18, deduce the type of emission. So if you look here, you would see that you had an electron coming off. That's beta decay. So you write beta decay on the line. If during the decay process, the energy liberated is 2.5 times 10 to the negative 14 joules, calculate the mass difference. Use Einstein's mass energy equation. So E is equal to mc squared. Therefore, M would be equal to E over c squared because we're looking for the mass difference. And it should be delta M. So E equals to mc squared. Therefore, the change in mass will be equal to E over c squared, where M, change in mass, is equal to 2.5 times 10 to the negative 14 joules divided by the square of 3 times 10 to the 8 meters per second. If 1 joule is equivalent to 1 kilogram meter squared over second squared, then kilogram meter squared over second squared times second squared over meter squared will give us kilograms. And then we get the answer 2.8 times 10 to the negative 31 kilograms. or we could rate it with 30 zeros before 2 and 8 kilograms. You could, if you want to be funny. All right, see you. Bye.